Atoms, the fundamental building blocks of matter, consist of a dense nucleus orbited by electrons. Within this nucleus reside protons and neutrons, collectively known as nucleons. While protons carry a positive electric charge, neutrons remain electrically neutral. One might expect the like charges of protons to repel each other, tearing the nucleus apart. However, a powerful force counteracts this repulsion: the strong nuclear force. This force, effective only at extremely short distances, binds nucleons together, forming the stable nucleus we observe. The energy required to fully separate the nucleons within a nucleus, effectively overcoming the strong nuclear force, is known as the binding energy. This energy represents the glue holding the nucleus together. A higher binding energy signifies a more stable nucleus requiring a greater energy input for disintegration. Conversely, a lower binding energy indicates a less stable nucleus, more prone to fission or radioactive decay. The concept of binding energy is crucial in understanding various nuclear phenomena, including nuclear fission and fusion. In fission, heavy nuclei like uranium are split, releasing energy corresponding to the difference in binding energies between the parent nucleus and the resulting daughter nuclei. Fusion, on the other hand, involves the merging of lighter nuclei, such as isotopes of hydrogen, to form heavier ones, again releasing energy due to binding energy differences. Understanding binding energy is fundamental to comprehending the stability of atomic nuclei and the energy released in nuclear reactions. It provides a quantitative measure of the force holding nucleons together and dictates the energy required to break them apart. This concept finds applications in diverse fields, from nuclear power generation to astrophysics, highlighting its significance in understanding the universe at its most fundamental level. Photons, the fundamental particles of light, carry energy and momentum. They can interact with matter in various ways, including absorption, scattering, and transmission. When a photon encounters a nucleus, it can transfer its energy, potentially leading to changes within the nucleus. However, this energy transfer is not arbitrary. It adheres to specific quantum mechanical rules. For a photon to induce changes within a nucleus, its energy must meet or exceed a certain threshold. This threshold is dictated by the specific energy levels within the nucleus, akin to the discrete energy levels available to electrons in an atom. If the photon's energy matches the energy difference between two nuclear energy levels, it can be absorbed by the nucleus, causing a transition between these levels. This process is analogous to how electrons in an atom can absorb photons and jump to higher energy levels. However, if the photon's energy is insufficient to bridge the gap between nuclear energy levels, it will not be absorbed. Instead, it may scatter off the nucleus, changing direction but not transferring significant energy. This is akin to shining light on a mirror. The photons are reflected without significantly altering the mirror's state. The interaction between photons and nuclei highlights the quantized nature of energy exchange at the atomic level. Photons cannot transfer arbitrary amounts of energy. Their interactions are governed by the specific energy levels within the nucleus. Understanding these interactions is crucial in various fields, including nuclear physics, astrophysics, and medical imaging, where photon-nucleus interactions form the basis for techniques like gamma-ray spectroscopy and PET scans. The deuteron, a simple nucleus consisting of one proton and one neutron, serves as a prime example to illustrate the concept of minimum photon energy for nuclear dissociation. To break apart a deuteron, a photon must possess sufficient energy to overcome the binding energy holding the proton and neutron together. This minimum photon energy, known as the threshold energy, is equivalent to the deuteron's binding energy. If a photon with energy below this threshold interacts with a deuteron, it will not cause dissociation. Instead, it may scatter off the nucleus or be absorbed, raising the deuteron to a higher energy level without breaking it apart. However, when a photon with energy equal to or exceeding the threshold, energy interacts with a deuteron, it can be absorbed, providing enough energy to overcome the strong nuclear force. This absorption leads to the deuteron's disintegration, separating the proton and neutron. The specific value of the threshold energy for deuteron dissociation is approximately 2.22 MeV, mega-electron volts. Photons with energies below this value cannot dissociate a deuteron, while photons with energies at or above this value can initiate the process. Understanding the concept of threshold energy is crucial in various applications, including nuclear physics experiments and medical treatments like radiation therapy. By controlling the energy of photons used, scientists and medical professionals can precisely target specific nuclei, inducing desired effects while minimizing damage to surrounding tissues. The law of conservation of momentum, a fundamental principle in physics, states that the total momentum of a closed system remains constant over time, even if internal forces are acting within the system. This principle applies universally, from collisions of billiard balls to interactions between subatomic particles, including photon-nucleus interactions. In the context of photon absorption and nuclear dissociation, conservation of momentum dictates that the total momentum before the interaction must equal the total momentum after the interaction. Since photons carry momentum, albeit a small amount due to their massless nature, this momentum must be accounted for when a photon interacts with a nucleus. Consider a photon striking a stationary deuteron. Before the interaction, the total momentum is solely due to the photon. If the photon is absorbed and the deuteron dissociates, the resulting proton and neutron will carry away the momentum initially possessed by the photon. This ensures that the total momentum of the system remains conserved. The conservation of momentum has significant implications for the kinetic energy of the resulting particles. Since momentum depends on both mass and velocity, a heavier particle will possess greater momentum at a lower velocity compared to a lighter particle. Therefore, in the dissociation of a deuteron, the neutron, being slightly heavier than the proton, will typically carry away slightly less kinetic energy than the proton, even though the total momentum is conserved. Understanding conservation of momentum is crucial in analyzing and predicting the outcomes of photon-nucleus interactions. It provides a framework for calculating the energies and momenta of the resulting particles, and ensures that the fundamental laws of physics are upheld at even the smallest scales. Section 5. Beyond binding energy. Accounting for kinetic energy. When discussing the minimum photon energy required to break apart a nucleus, it's crucial to consider not only the binding energy holding the nucleus together, but also the kinetic energy imparted to the resulting particles. The conservation of energy dictates that the total energy before the interaction must equal the total energy after the interaction. Therefore, the minimum photon energy required for nuclear dissociation must account for both the binding energy and the kinetic energy of the resulting particles. This means that the photon's energy must exceed the binding energy by an amount equal to the kinetic energy imparted to the separated nucleons. The kinetic energy of the resulting particles is not fixed and can vary depending on the specific interaction. Factors influencing the kinetic energy distribution include the angle at which the particles are ejected and any internal excitations within the nucleus before dissociation. In some cases, the photon's energy might only slightly exceed the binding energy, resulting in the separated nucleons having minimal kinetic energy. Conversely, a high-energy photon can lead to significant kinetic energy being imparted to the particles, causing them to fly apart with high velocities. Understanding the interplay between binding energy and kinetic energy is crucial for accurately predicting the outcomes of photon-nucleus interactions. It highlights that the minimum photon energy for dissociation is not simply a fixed value, but rather a threshold that must be surpassed to account for the energy needed to overcome the binding force and impart kinetic energy to the resulting particles. Section 6. Real-world applications, from astrophysics to medical imaging. The concepts of binding energy, photon-nucleus interactions, and conservation laws are not merely theoretical constructs. They find practical applications in a wide range of fields, impacting our understanding of the universe and driving technological advancements. In astrophysics, the study of nuclear reactions in stars relies heavily on these concepts. The energy production in stars stems from nuclear fusion, where lighter nuclei combine to form heavier ones, releasing tremendous amounts of energy in the process. Understanding the binding energies of different nuclei is crucial in modeling stellar evolution, predicting the types of elements produced and estimating the lifespan of stars. Medical imaging techniques such as positron emission tomography, or PET scans, utilize photon-nucleus interactions for diagnostic purposes. In PET scans, radioactive isotopes that emit positrons are introduced into the body. When a positron encounters an electron, they annihilate, producing two gamma rays that travel in opposite directions. Detecting these gamma rays allows for the localization of the radioactive tracer within the body, providing valuable information about metabolic activity and disease processes. Furthermore, radiation therapy, a common cancer treatment modality, relies on the controlled delivery of high-energy photons to target and destroy cancerous cells. By carefully calculating the appropriate photon energies and dosages, radiation oncologists aim to maximize damage to tumor cells while minimizing harm to surrounding healthy tissues. These examples highlight the far-reaching implications of understanding photon-nucleus interactions and the associated concepts. From unraveling the mysteries of the cosmos to advancing medical treatments, these fundamental principles play a crucial role in shaping our understanding of the world around us. Section 7. Summary, Key Takeaways, and the Bigger Picture. This exploration into the realm of photon-nucleus interactions has illuminated key concepts that govern the behavior of matter at the subatomic level. We've delved into the significance of binding energy as the glue holding nuclei together, the quantized nature of energy exchange between photons and nuclei, and the critical role of conservation laws in these interactions. The minimum photon energy required to dissociate a nucleus, exemplified by the Deuteron, highlights the importance of overcoming the binding energy and providing sufficient kinetic energy to the resulting particles. This threshold energy dictates whether a photon can induce nuclear disintegration or merely cause excitation within the nucleus. The conservation of momentum ensures that the total momentum of the system remains constant throughout the interaction, influencing the distribution of kinetic energy among the resulting particles. Understanding these concepts is not merely an academic exercise, but rather a gateway to comprehending a wide range of phenomena, from the energy production in stars to the diagnostic power of medical imaging. As we continue to probe the intricacies of the subatomic world, these fundamental principles serve as guiding lights, illuminating the path towards unraveling the mysteries of the universe and harnessing its potential for the betterment of humanity. Section 8. Further Exploration, Delving Deeper into Nuclear Physics. For those eager to delve further into the captivating realm of nuclear physics, numerous avenues await exploration. Diving deeper into the subatomic world reveals a tapestry woven with intricate forces, peculiar particles, and mind-boggling phenomena that continue to challenge our understanding of the universe. One path leads to the exploration of different types of nuclear reactions, each governed by its own set of rules and producing unique outcomes. From fission, where heavy nuclei split apart, to fusion, where lighter nuclei combine, the diversity of nuclear reactions offers a glimpse into the immense energy stored within the atom's core. Another avenue involves investigating the bizarre world of subatomic particles. Beyond protons and neutrons lie a plethora of particles with exotic names like quarks, leptons, and bosons, each playing a distinct role in the intricate dance of subatomic interactions. Unraveling the properties and interactions of these particles holds the key to unlocking a deeper understanding of the fundamental building blocks of matter. Furthermore, the study of nuclear physics extends beyond the confines of our planet, reaching into the vast expanse of space. Astrophysicists rely heavily on nuclear physics to comprehend the life cycle of stars, the origins of elements, and the workings of celestial objects like pulsars and black holes. By studying the cosmos through the lens of nuclear physics, we gain insights into the universe's grandest events and the processes that shape the world we know today. Section 9. Glossary, Defining Key Terms for Clarity. To ensure clarity and facilitate further exploration, let's define some key terms encountered throughout our journey into the world of photon-nucleus interactions. Nucleus. The dense, positively charged center of an atom, composed of protons and neutrons. Nucleon, a collective term for protons and neutrons, the particles residing within the nucleus. Binding energy. The energy required to completely separate the nucleons within a nucleus, overcoming the strong nuclear force. Photon, the fundamental particle of light, carrying energy and momentum. Deuteron, a simple nucleus consisting of one proton and one neutron, often used as a model system in nuclear physics. Threshold energy, the minimum energy required for a photon to induce a specific nuclear reaction, such as dissociation. Conservation of momentum, a fundamental law of physics stating that the total momentum of a closed system remains constant over time. Kinetic energy, the energy possessed by an object due to its motion. Fission, a nuclear reaction where a heavy nucleus splits into lighter nuclei, releasing energy. Fusion, a nuclear reaction where lighter nuclei combine to form a heavier nucleus, releasing energy. This glossary provides a starting point for further exploration, equipping readers with the vocabulary needed to navigate the fascinating world of nuclear physics and its profound implications for our understanding of the universe.